Have you ever wondered if there's a kind of secret language, a hidden code that's running pretty much everything? From your phone to the global economy? Well, there is. And today, we're going to crack that code. So let me ask you this. What in the world connects 3D movies, those big economic forecasts, and yeah, the search engine you probably use to get here? It sounds kind of random, right? Let's look at a few things. Okay, first up, analyzing the stability of a bridge. I mean, how do we know a bridge isn't going to collapse? It all comes down to making sure the system of forces holding it up is, well, consistent. Any little inconsistency could be a huge red flag for instability. Or how about this? The magic behind Google. You know that algorithm that sifts through billions of websites in, what, a fraction of a second to give you the perfect result? And finally, think about the graphics in your favorite video game. You know, the ones that are so mind-blowingly realistic. So a bridge, a Google search, a video game. The answer, the single thread connecting all of them? It's matrices. Okay, so what is a matrix? Don't let the name intimidate you. At its core, it's just a simple grid of numbers, arranged in rows and columns. That's it. But, and this is the crazy part, this simple grid is one of the most powerful tools ever invented for organizing and, more importantly, manipulating really complex information. So let's open up our matrix toolkit. The very first thing we're going to pull out is this incredible ability to act like a diagnostic tool. It can take a snapshot of a system, and I mean any system, and tell us if it's healthy, if it's stable, if it even makes sense in the real world.
And this tool is called rank. Here's a simple way to think about it. Imagine you're trying to solve a puzzle, but someone gave you 3 clues when you only needed 2. One of those clues is probably just repeating information, right? It's redundant. Well, rank is what tells us exactly how many unique, totally essential pieces of information we're working with, and how much is just, noise.
And why does this matter? Well, it tells you everything. A high rank? That's great news. It means your data is solid, you've got unique info, and you're pointing toward one single stable solution. But a low rank? Oof, that's a red flag. It means you've got repetitive data, which could lead to an infinite number of solutions, or even worse, it could mean the whole system is just plain unstable. So this all leads to the one big question that engineers and scientists are constantly asking themselves. Is my system consistent? It's a fundamental check. They use matrices to see, is this bridge design even possible in the real world? Can this electrical circuit actually function? Is this economic model where supply and demand meet actually feasible? It's a reality check. Here's the bottom line. Matrices are basically an early warning system. We're talking about finding a fatal flaw in a bridge design before a single piece of steel is ever ordered. A matrix can analyze the whole system and scream, hey, there's a problem here. It literally prevents disasters before they even have a chance to happen. All right, so that's stability. Pretty cool, right? But let's grab the next tool from our toolkit because this is where things get even more interesting. We're moving beyond just taking a static snapshot. Now we're going to uncover the deep dynamic properties of a system, what you could literally call its fundamental DNA. And this brings us to 2 words that sound super complicated, but the idea is actually beautiful: eigenvectors and eigenvalues. Just picture this. You have a big rubber sheet, and you stretch it. Almost every point on it moves and changes direction, but there will be a few special lines that only get stretched or shrunk. They don't change their direction at all. Those are the eigenvectors. They're like the unshakable skeleton of the system, its DNA. And the eigenvalues? They just tell us how much stretching or shrinking happened along those lines. So what does that really mean? Well, they point to the directions a system naturally wants to move in, the directions it wants to stretch or shrink or vibrate. This is huge for an engineer. They can use this to find the exact frequency a bridge will naturally start to vibrate at. And knowing that, well, that's absolutely critical to making sure it doesn't fall down. Now, you might be thinking, how on earth do you find these things? Well, there's a whole process for it. Don't worry, we're not going to dive into the nitty-gritty math, but just know it's like following a treasure map. You follow the steps, and they lead you straight to the heart of the system, revealing this crucial DNA, those eigenvalues and eigenvectors. And this is where it gets absolutely wild. This one idea, eigenvectors, is everywhere. It's the secret sauce behind Google's PageRank. It's how facial recognition software works. It's deep in quantum mechanics defining energy levels. It's even how we compress images to make file sizes smaller.
It's just mind-boggling.
Let's stick with Google for a second. Imagine the entire internet as one gigantic matrix, where every link from one page to another is recorded. Okay? The most important eigenvector of that massive matrix gives every single web page a score. A page that has a high eigenvalue is seen as more important, more authoritative. And that, my friends, is why it pops up at the top of your search results. It's all just one giant eigenvalue problem.
Okay, so far, we've seen how matrices can describe and analyze things, right? They're like a super-powered magnifying glass. But now for our final tool. This one is different. This is where matrices stop just looking at the world and start changing it. We're talking about using them as active creators to manipulate data and build whole new realities.
Yeah, think about that. Matrices aren't just for analysis. They are for action. They're not just observing the world. They're the engines that make things happen in our digital lives. I mean, every single time you pinch to zoom on a photo on your phone or rotate an image, bam, a scaling or rotation matrix is doing the work behind the scenes. When you send a secure message, you bet an encryption matrix is scrambling that data into a secret code. And the craziest part? All of these complex actions are just powered by simple matrix multiplication.
And of course, if you can do something, you need to be able to undo it. To decrypt that secret message, for instance, you need to find the inverse of the matrix. It's literally the undo button for whatever action you just performed. Now, finding that can be tricky, but don't worry. Mathematicians have figured out some really clever shortcuts to make it happen.
And this power, this ability to act, is literally what builds the world we live in. Those incredible 3D models in movies and video games, matrices. The neural networks behind the AI that's changing everything, trained with matrices. The cryptography that keeps all our digital messages safe, yep, you guessed it, that's built on a backbone of matrices too. So let's pull it all together. Why do matrices run the world? Because, as we've seen, they're not just some dusty abstract concept from a math book. They're a master toolkit for understanding and shaping our incredibly complex world. I love this analogy. They're like the Swiss Army knife of mathematics. You've got one tool to check a system's health and stability. You've got another to uncover its hidden DNA. And you've got another to actually transform data, to build and secure the digital reality we all live in. It's the whole package. So think about it. From the structural integrity of the very building you're in right now, to the search results on your screen, to the encryption that's keeping the device you're using secure, matrices are everywhere, working silently in the background. So here's a thought to leave you with. What unseen matrix is shaping your world right this second?